Oh, hello again. Now, as I promised, this is the second part of the same lecture, and here we will discuss a generalization of Euler's theorem. Euler's theorem, abbreviated ET, is A, P, N is congruent to 1 more than. Where A is coprime, A is coprime to N. Right? Now, how can we think of this statement algebraically? Well, A being coprime to N simply means that A is in the unit group. Okay, so this being coprime means that this is in the unit group, and phi n is simply the order of the unit group. So now what we're saying is that in the unit group, if we take any element and raise it to the power of the order of the group itself, we get 1. But this is a consequence of Lagrange's theorem. So Lagrange's theorem, Lagrange says that given a finite group G, the order of an element in this group divides G. Well, the order is the smallest positive number, such that if you raise G to that power, you get the identity. This G is not necessarily a generator, so there is no assumption about G being an abelian group or a cyclic group. There is a general statement about which applies even to non-commutative groups that I didn't discuss in this class, but this is a general statement. So if you take this theorem and consider this power of G, well, the order of G divides, suppose the order of G is some M, right? So M divides this G. So this means that this is Gm S, but Gm is 1. So you simply get 1, and this is the statement of Euler's theorem. So Euler's theorem itself is an easy consequence of Lagrange's theorem. On the other hand, we know quite a bit about the unit groups, so let's try to use our knowledge of the unit group with a little bit of abstract algebra to come up with a strengthening of the statement of Euler's theorem. Alright, so what do we know? We know that if n is a product of prime powers, so P, S, E, S, then this un is isomorphic to U, PS, ES. Okay? Now, what else do we know? We know that if P is 2, then U2E is congruent as a abelian group. It's a direct product. So assuming E is larger than 3, if E is 2 or 1, you're getting either the trivial group or the cyclic group of order 2. And for the prime power, odd prime power, as I said, you get a cyclic group of order phi PE, which is just the cyclic group of order P E minus 1, P minus 1. Right? So we know that this UN is a direct product of almost cyclic groups. Well, cyclic groups when you have odd primes, and and almost a cyclic group if one of the primes is 2. All right, now the abstract algebra fact that we need is the following. Let me erase this. So suppose we're given some integers, consider the following group. Consider G, which is a direct product of S cyclic groups, and the order of each cyclic group is mi. We can ask the following question. What is the order, what is the smallest number that kills every element in this group? Right? Well, the smallest number that kills every element in a cyclic group is the order of the group itself. But if you have a direct product of cyclic groups, you just need a number that is divisible by the orders of all the cyclic groups. So the fact from linear algebra that we need is that, well, first let me give a definition. The exponent of G is the smallest positive integer, e.g., such that G e.g. is equal to 1 for all G in G. Okay, so the exponent of the group is the number that kills every element in the group. And then if you want to find the exponent of a cyclic group, that is easy. Example, the exponent of a cyclic group of order m is just m, because the generator has order m. And then every element, of course, has order dividing m. So this is easy. But what about a product of cyclic groups? If you think about what this number does, it's just the smallest number such that you can use it to kill every element in each cyclic group individually. But that, since the exponent of this group is mi, right, we need a number that is divisible by the exponents of each individual direct factor, and the smallest such number is the least common multiple. The theorem is that the exponent of this G, exponent of the direct product is equal to the least common multiple of M1 to MS. And the proof is essentially what I said. I'll leave the proof to you. Okay. So if we take an example, well, suppose I have a group of order. Suppose I have this group C. G is C3 cross C6, right? So the LCM is of course 6, but if I take any element in this group, G1, G2, and I raise this to 6 power, I will get G1 6, G2 6, right? And G1 has order dividing 3, so this is 1, and G2 has order dividing 6, so this is also 1. So I get 1, 1, which is the identity in this group. All right. So now let's apply this theorem to the unit group. If we apply this theorem, well, before applying this theorem, what is the generalization of Euler's theorem? The exponent of the group is a number that kills every element in the group. So this means that A, E, UN is congruent to 1 mod n. Okay? And the exponent of the group is, of course, divides the order of the group. This simply follows from Lagrange's theorem. So the fact that the exponent of the group can be significantly smaller than the order of the group is the generalization of Euler's theorem. So what is E UN? Well, by the theorem is the LCM of phi P1 E1 phi P S ES if all these primes are odd, if P1 PS are odd, and if let's say P1 is a power of 2, then this is equal to the LCM of 2 E1 minus 2 phi P2 E2 phi PS ES. So if P1 is 2. And of course phi PS phi PE, right, is P minus 1, P minus 1. And you immediately see that this number is usually smaller than the order of the group because, for example, all P1 minus 1, if P is odd, are even numbers. So 2 appears redundantly in all these numbers, and so this number will be usually smaller than the Euler number. Let me finish with an explicit example where you see this how this works. Right, so the example we take n to be 16 times 7 squared times 3. All right. Now EUN in this case is the LCM of 4, which comes from 16. Well, before doing this, let me go back and write down what this is isomorphic to. So this is U16 times U3 times U7 squared. Now, what is each of these group as a abelian group? Well, the 16 group, this is isomorphic to C2 cross C4, right? And then this is isomorphic to C2 again, because this is a prime. And then this is isomorphic to a cyclic group 7 times 6, which is the Euler number of 7 squared. All right, so now having this decomposition, if we apply that abstract algebra theorem, the exponent of UN is the LCM of 2, 4, 2, 7 times 6. Alright, what's the LCM? Well, these 2's are redundant, and there is a 2 here. And you get that the LCM is 4 times 3 times 7, which is 84. If you compare this to the Euler number, this is much smaller. So, in fact, so in the book, the notation for the exponent of un is abbreviated to en, and now phi n, if you compute the Euler number, well, you get 8 times 3 minus 1 times 7, 7 minus 1, and this is 672. And the conclusion, the generalization of Euler's theorem, would be that A84 is congruent to 1 mod whatever this n is, instead of A to 672. And you can easily check that 84 divides 672. Now, why is this useful? This is useful if you want to compute some explicit power of a number that is coprime to n. So if we take suppose we want to compute 5 to power 86 mod n, where n is as before. So this is 16 times 3 times 7 squared. Well, you cannot apply Euler's theorem to compute what this is, because 86 is less than 672. So Euler's theorem doesn't give you any simplification. On the other hand, if you use this fact, you observe that so 86 is equal to 584 times 5 to 2, but then 5 to 84 is congruent to 1 modulo n. So overall, this is congruent to 25 mod n, which is quite simple. So this is the generalization of Euler's theorem, and one of the exercises, I think, asks to compute the exponent of a unit group. So the exponent is, as I explained a minute before. So this concludes today's lecture, which was a bit longer than a usual lecture, but this is a video lecture, so you can watch it in parts. All right, see you on Monday.